Hi everyone. Welcome to this supplementary video. This supplementary video basically walks you through the calculation of Stokes drag. And the idea is that this is a problem that we have done in the class, and we went till we found velocity profiles, and then the goal was eventually the goal was to calculate drag force, which will have combinations of both pressure and shear stress forces. So that is what we essentially want to focus on and do in this video. So I will not go through the derivation of velocity profiles. That is something we have already done in class. But just to quickly recap, we used the stream function approach because we have a bidirectional system. So we used E for psi is equal to 0, and because the system X is symmetric about phi, then we decompose psi into phi r times sine square theta, and then we derived the velocity Vr, V theta, and then the pressure by substituting back into the Navier-Stokes equation. So that is something we already discussed in class. This video will specifically focus on the topic of Stokes drag. So let's go through it. And always remember that whenever you have drag forces, and something we have discussed many times, you want to have fluid. So first, the fluid will want to point into the fluid. So if you have into the fluid, your N is clearly E of R, right? So your N is clearly E of R. So N is equal to E of R. Okay, so this is pretty clear because the normal to the surface of the sphere points into the fluid, that's E of R. Then how to choose ds? This is something we have discussed now several times, that the ds is determined by what coordinate is constant. On the surface, the coordinate that is constant is small r is equal to capital R. And so you look in the appendix and look for a differential element area. And if you do that, this is equation 8.743. This is 8.743. And ds is equal to capital R square sine theta d theta d phi. Okay, so note that it is r square sine theta d theta d phi. I have used small r as capital R because we are on the surface of the sphere. So if you look in the book, this is 8.743. It is a small r, but small r is equal to capital R on the surface. So that's why the ds is like that. Then the third element before we integrate, and note that theta will go from 0 to pi and phi will go from 0 to 2 pi. And this is the way you define spherical coordinates, that you go from, theta goes with the angle of z, and phi is along the circumference, so it goes from 0 to 2 pi. All right, so then we have the stress vector. Recall the stress vector is given by n dot sigma. Okay, and sigma is given by minus p plus tau, right? Now here we don't have the phi direction, so we just have r and theta. So it's a bit easier to do that way, that we can just make it a 2D matrix. So this is something we have done before, and I will just skip a couple of steps here because I think you've had a decent amount of practice now with this. Okay, so this is the 2D matrix. So you have minus p plus tau. Now I have already summed them, and I've only done an r and theta because phi is 0, so it's just a 2 by 2 matrix. And then you will again multiply with this, and then have the first element and sum, and then the first element would be minus p plus tau rr. The second element, then you will multiply with this, and it will be tau r theta. Okay, so this is what you get, and essentially the final answer becomes S of n is minus p plus tau rr e of r plus tau r theta e of theta. Okay, so this is the portion we get. And now at this point, it might appear that, okay, we have everything. Should we just solve it? But what we do not yet know is the tau rr and tau r theta. Pressure we know. Pressure we already know at the surface. So pressure at the surface, pressure at r equal to capital R, which is at the surface, is known. That will be minus 3 by 2 mu u by r cos theta. I just want to show that I have just substituted small r is equal to capital R in the pressure formula here, which you see on the screen. And I just substituted small r is equal to capital R because we are at the surface. The pressure is this, but we still don't know tau r and tau r theta. And how will we do that? So to always, whenever you get these variables, just look in the formula in the table for the book for tau RR. So the table in the book is, let me make sure I get it right, 6.6, table 6.6. And that tells us that tau RR is 2 mu del V R by del R at R is equal to capital R. Okay, so that's the first thing. So that's the viscous stress at the surface. And we basically differentiate this term. So you already know the VR. So we'll differentiate by small r and then put small r is equal to capital R. So we will get 1 u cos theta. So you'll get u cos theta. The first term goes away because you can't differentiate, it's just 1. Then we have minus 3 by 2 r by small r. So it will become plus 3 by 2 r by r square. Okay. And then the last term will be 1 by 2 r by r whole cube. So we'll make it minus 3 by 2 r cube by r4. And this is multiplied with u cos theta. And this is at r equal to capital R. Okay. So this is clear. You just basically differentiated. I just differentiated the VR with R. And when you substitute, this goes away and this goes away. And this comes out to be 0. Tau RR is 0. Okay. I should note that in your homework problem, problem 4 of homework 4, your normal stress may not be 0. So, don't jump to assuming that something is 0 or non-zero, because it's a bidirectional problem. There is no scale difference. Everything will have the scale by radius R. So make sure you are, solving for the variables before jumping to any. So tau R theta in the book, if you look at the table, it is mu R del by del R of v theta by R plus 1 by R del v R by del theta. Okay, so this is exactly the formula given in the book. And you have evaluated this at R equal to capital R. And I'll skip a couple of steps here, and this is just so that you don't have, I don't make the video too long, but essentially this would come out to be 0. And the final result you will see will be 1 minus 3 by 2 mu u by r sine theta. Okay, so let me make sure this result is correct. You do get minus 3 by 2 mu u by sine theta. Okay, so we have the stress vector now. The stress vector is minus 3 by 2 mu u by r cos theta er, and then minus 3 by 2 mu u by plus here minus 3 by 2 mu u by r sine theta e theta. Okay. Other way to write this thing is actually a little bit easier. You see, you just take out this 3 by 2 mu u by r factor and write this as cos theta er minus sine theta e theta. Okay, so this is the value of stress vector. And what we now need to find is the force. So we have done the force fully now. So let me just take out this 3 by 2 mu u by r. So note that now I will be substituting stress vector here. Sorry, stress vector here times ds. Okay, so this is now the plan. So we get 3 by 2 mu u by r. Then we'll say cos theta er minus sine theta e theta. Okay, and so this is the part, and then we have r square sine theta d theta d phi. Okay, so this is our equation. Now, the common tendency at this problem is part is again to just directly integrate, and as we have discussed several times, you can't directly integrate. You have er and e theta. Both of the directions are changing. They're curvilinear, so we have to substitute them back in ex and ey. And if you do that, this is 8.7, 38 and 39a, 8.7, 38 and 8.739. 738 and 39. 8.738, 8.739. Okay. If you do that, then what you will find is that we'll say ER is sine theta cos phi ex, sine theta cos phi ex, phi ex plus sine theta sine phi ey. Let me check. Yes, plus cos theta ez, and then we have e theta as cos theta cos phi ex plus cos theta sine phi ex, and then minus sine theta ez. So you can't directly integrate unless you bring it down into Cartesian coordinates, which you can do. So now you can put this back and substitute it in the solution. So 0 to pi for sine theta and 0 to 2 pi for cos theta. Okay. Now, this is again something I'm skipping over. It's not very hard. If you just substitute ex, ey and collect them, what you will find is that the ex and ey terms will go away. So what I'm saying is you will get an expression here, something like 3 by 2 mu u r 0 to 2 pi, 0 to pi, and you'll have something ex, and then sine theta d theta d phi ex plus 0 to 2 pi, 0 to pi, sine theta d phi ey plus 0 to 2 pi, 0 to pi, and then you'll have sine theta d phi ez. So please do go through this exercise. It's very instructive, and I am skipping over some of these steps again in the interest of time, but these will come out to be 0. They will be identically 0, which kind of makes sense because the flow is happening in z direction. Everything across the x and y plane is 0, but you will show you get that identically from this approach. Okay. Now, when if that is the case, then if we see the z component here is cos theta, and the theta z component in e theta is minus sine theta. So I'll get a cos square theta plus sine square theta, which is kind of amazing that here actually the ez term is simply plus cos square theta plus sine square theta. Okay. And then this is equal to obviously 1. And then so you get f is equal to 3 by 2 mu u r 0 to 2 pi 0 to pi sine theta d phi ez. And finally, this will become 3 by 2 mu u r 2 pi because there is no dependence on phi, then 0 to pi sine theta d theta ez, and then this will essentially give you an answer of 2. So what you'll finally get is 6 pi mu u r 6 pi mu u r ez, which is the celebrated Stokes drag result. Okay. So just to quickly recap how we approach this problem. The way we approach this problem is we first started by defining the differential element of surface area, the normal vector which points into the fluid, and the stress vector which we then calculate by using the matrix multiplication. Then we calculate tau rr and tau r theta. Tau rr was 0, tau r theta had a value. Please verify that you are able to get this value. Pressure we already had the value. Then we said we had the stress vector which we substituted, and then we got the result in ER and E theta, but we can't directly integrate because we have to substitute in forms of EX, EY, and EZ, which when done, EX and EY come out to be 0. You're only left with EZ. And then finally, when you do that, you get to the celebrated result of Stokes drag. Okay. So I hope this video was useful, and I look forward to seeing you in the next video.